Welcome back everyone to the second talk. We have Hongdi Huang from Shanghai University.
Thank you, Linda. First I want to thank Amy and Miriam for the invitation and speak here. This is my very first trip to Europe, so I'm happy to be here. Now this work is going with Xin and Cindy and James. James is here. So I will talk about from three parts. Let's first give some motivation why I'm very excited about this topic, and second, I will give some characterization of the automorphism group of some Poisson algebras. So last, I will introduce the tool to be applied to do this project. So for many, for different people, people have different reason or have different interest in why we think automorphism group is important. At least for myself, I think in particular, people like me study both algebra, so we think the automorphism group can capture algebras symmetries. So another thing is that whenever we want to say we want to do classification of algebra, one classification is use the isomorphism equivalence. Another thing is that the automorphism always try to help us to see the hidden algebra structure, like centers, ideas. Of course, from algebra geometry, like for example, the variety, we want to understand the automorphism of variety. We can simply try to study the automorphism coordinate algebra. Okay. Another thing I would very excited to say as application of automorphism group. This is one new result from our lesson in the table. So we use the automorphism group to characterize when an algebra is a polynomial algebra. So here we do use an invariant which is relative to the automorphism group. We see algebra A has a subspace V. If V is order stable, which means after you apply the automorphism image, so the image is still contains V. So in this case, we say V is order stable. So our result is say suppose our field is algebraic closed and have zero characteristic. In this case, for an algebra, here we even don't need to say we don't even require A is a commutative algebra. So we show that A is a polynomial with more than two variables, and if only if this satisfies the following two conditions. The first one is say A of course cannot be equal K, and A is connectively greater than F1. Second is that we say A doesn't have any non-trivial order stable space. So this result tells us some information. The automorphism group of algebra do have the important applications.
So A is greater there. What is the assumption now?
A is just the algebra. Right? A is just the algebra.
Being graded is the property, not a, sorry, it's structure.
It's just A, which means the A you can write like AI, like it's a direct sum of AI. I is here. Let's say I is from it's just integer, and AI times AJ is contains AI plus J. So connecting just means that zero pieces is it's just K.
Condition one is there exists a gradient.
So, sorry,
Addition one is there exists a gradient.
yes, it is bigger.
But the automorphisms don't respect the gradient.
We do need to use, because this is sufficient condition, right? We do need to use big constraint to get it. And otherwise, it cannot be.
Automorphisms of gradient.
Automorphism is just the end automorphism. Yeah, not required. All right, so, okay, so actually automorphism group, I mean, to understand this topic, we don't, it doesn't require too much information. However, even for a polynomial algebra, the automorphism group is still very complicated. It's not something, okay, the topic is easy to state, but it's a far less, I mean, it's less know about this automorphism group, even for polynomial. So there's a breakthrough result, say, for polynomial with the three variables, and the automorphism group is not attained. So let me first introduce what means tamed or wild here. For any polynomial in Kx with n variables, if the map is either a found or triangular, so which has this form, so say A, first one, just say A is a linear, second is just say A here. Also, people maybe call an arithmetic transformation. So in these two cases, if any automorphism is generated by these two types of morphism, we call this automorphism is tamed. So if the automorphism is not tamed, then we call automorphism is a wild. So for the simple case, like Jacobi conjecture, people usually work in the n equal 1, n equal 2, right? So for n equal 1, we know the automorphism group is tamed, and n equal 2 is also 2. And this was now in a very early time, and in 2004, and Schwarzbach and UMB show that there exists automorphism which is not tamed, so which is given by the so-called Nagata automorphism. So this Nagata automorphism has a particular form, which is given in this form, and we just like the popular counter example of a Jacobian conjecture. So it has a particular form. So we can see this automorphism has two properties. One is sigma fixed state, another is sigma definite figure omega. So actually, inspired by this automorphism, actually we can construct a family automorphism which looks like a Nagata. So which means this is the automorphism of a polynomial in three variables, but it fixes one variable x or y, and besides it fixes another irreducible homogeneous polynomial, or just an irreducible polynomial here. So inspired by this one, we try to say, right now we know in three variable polynomial, the automorphism is not tamed, but it's possible try to enlarge a little bit the set, the generator set, such that say I try to include automorphism, the Nagata type of morphism into my generators. So in this case, can we say all of the automorphism in three variables, which is just the, I mean, all of the generators just those 10 plus Nagata type. So that's our thinking. So inspired this example, we try to say let's expand the family of generators. we try to pick up a special type of automorphism now we call pivotal, which is say here I just give an example for 3 variable, but for more than 3 variable, we can mimically divide the automorphism fixed to irreducible polynomial f1 and f2. So if eta calls pivotal can, which means eta can generalize by such pivotal automorphism. So the question is that we know the automorphism of 3 variables is not a term, but it's possible pivotal term. Okay, so to do these questions, we can go back to the Nagla type. So our automorphism fixes G and omega, right? So in this case, we try to pay our attention from the polynomial into polynomial of Poisson polynomial algebra. So here I say instead of trying to answer the previous question, we try to investigate these questions. What's the Poisson automorphism of a unimodular Poisson algebra KXYZ? Let me tell you what is a Poisson algebra and what is a unimodular Poisson algebra here. Here we say a Poisson algebra, which we set up as a commutative algebra and with a Lie bracket. And this Lie bracket is compatible with our multiplication, which is called satisfies the Leibniz rule. Here, in particular, in our project, let's just fix a polynomial, Poisson polynomial with the 3 variables. So the 3 variables, because we give a weight, which is say for x, y, z, we give a degree ABC. So ABC is actually natural integers. Of course, we can assume there's a order in ABC. And the Poisson bracket, which is just determined by homogeneous polynomial omega. In particular here, in our case, in 3 variables, then this definition is equivalent to the general definition of a Poisson structure. So here, xy, the bracket of xy, which is given by the partial of omega with respect to z and such. So a Poisson algebra has this kind of Poisson structure we call unimodular. I mean, in general case, the unimodular Poisson algebra is defined in another way, but for the in 3 variables, these 2 definitions are equivalent to each other. Okay, so for example, if we give x, y, z has a degree 1, 2, 3, and omega is a homogeneous degree element with a degree 6. So in this case, my A polynomial has a Poisson structure given by this omega. In particularly, so actually, as I said, we want to try to understand the automorphism of some Poisson algebra. Why? Because what the automorphism group may vary a lot if the omega are very different. So the easy case is when the omega has a nice property, which say the partial of the omega with the partial with respect to x, y, z, and we get a 3 equation. If the 3 equation has trivial solutions, in this case, we call omega has isolated singularity. So there are several equivalent definitions for the other one. So in this case, we call A omega is a elliptic Poisson algebra. In particular, this is the example. The nice result is if at the beginning we said x, y, z has actually degree, right? But actually, after the classification, we can notice that only when A, B, C has this 3 pattern values, isolated isolated potential omega exists only in these three cases. And we actually give a classification of those three family because the lambda is a parameters. So we have a three family. So in this talk, I will introduce the automorphism only for this type of Poisson algebra. So let's go back to the original questions. What's the automorphism group of the related type of Poisson algebra?
Sorry, can I ask one question?
Yes.
When you have it, say, the degree DDD, as before, is the previous slide,
Yeah.
does it make a difference what D is? What-
It won't make a difference up to, I mean, in isomorphic case.
So this could in practice be 1, 1, 1.
Yes, 1, 1, 1, 1, 1, 2, 1, 1, 1, 2, 3. Okay, so let's first try to see recall the definition of Poisson automorphism. So basically, first the F must be algebra of automorphism and compatible with the Poisson structure, which is say F with the bracket AB will be equal to the bracket of FAFB. In this case, we actually prove that if the underlying algebra A is the same, but the Poisson structure are given by two different omega, like omega 1, omega and omega prime. If algebra automorphism, so these two Poisson algebra isomorphic to each other, if only if they exist algebra automorphism such that the two potentials, the potential like 5 omega prime, and the difference is just the scalar of the determinant of 5, because by the Jacobian conjecture we know 5 is automorphism, the determinant must be constant. So that here you can divide the constant. So the determinant of 5 is a constant, non-zero constant. In particular, if we say omega equal omega prime, then we can get the Poisson automorphism group, which is just a set. So first 5 is the algebra automorphism, and 5 almost fixed omega, right? So from here we can go back to our original questions. Our original questions say we want to understand the pivotal automorphism. What is the pivotal automorphism? Pivotal automorphism, which is just is an automorphism but fixed to irreducible polynomial, right? So we look at omega as a irreducible polynomial. Here omega is a irreducible polynomial. Then 5 almost fixed. 5 is almost fixed omega, right? So in this case, that's why I say to look at the polynomial automorphism, let's try transfer our attention to the Poisson algebra automorphism. For the first cases, if omega is given by the one of the particular situations, so here we know the automorphism group is classified, and very nice case is the Poisson automorphism group, which is exactly the greater Poisson automorphism group, which means that every automorphism is greater, preserve the degree. So in this case, once the automorphism is a greater automorphism, I mean, the group will become much smaller, because here just a subset of the 3 copies for the multiple cube of K. And in particular, okay, so here in this result, what happened? Oh, this I think I may go to the wrong direction.
Which one?
I go too fast. Okay, so. It doesn't work. Oops.
Maybe you can use computers.
I think so.
Great.
Oh yeah, that's my slides. So for the previous case here, they pretty much use the computation way to calculate the automorphism group. But for another two cases, because we just said there's three different family of elliptical Poisson algebra case. So now for another two case, we get a not very surprise different automorphism group from this example. Let's see. So we can classify. If first we only let's first look at my p omega. What is the p omega? Here, a is a polynomial. A is a polynomial with a three variable p, which is use a module mod out my sigma omega. In this case, p has a GK dimension 2, so it's relatively smaller than the a. And then in this case, we can classify the classify the automorphism group of p omega for the two different family, and which is given by the short exact sequence. So but our goal is try to understand the automorphism of automorphism group of A omega, not P omega. Instead of that, we need to understand another family of Poisson algebra, which is given by the quotient A quotient of the sigma module cos. Cos is just a constant here. If cos equals 0, then that's P omega. But in general case, we assume cos is not equal to 0. And in this case, we can show that every Poisson automorphism of P omega is greater, but every Poisson automorphism of P omega minus cos, which is linear. So what is linear? Linear means, for example, phi can send x. If x has degree 1, then phi send x kx plus k. I mean, the second part has a degree less than the first part. And in this case, we can try to lift our automorphism from P omega and P omega minus cos to the A omega. In this case, we show that every automorphism of A omega is graded. In particular, we can write the automorphism group explicitly. Here, I just not listed the explicit information. So finally, we can prove that those three like P omega and A omega, the Poisson automorphism group are isomorphic to each other. In particularly, they are isomorphic to the great automorphism great automorphism case. So once we get the, every automorphism is graded, then this automorphism group can be relatively smaller, right? So this is our final result. And but here we do assume omega has a there's a requirement for the degree of omega, which is a plus b plus c. But if my omega has a degree which is bigger than a plus, again, not equal a plus b plus 3, but it should be bigger than 5, then we also can get a similar result, say a omega and a omega, the automorphism group and the greater automorphism groups are the same. And actually, the automorphism group is a finite subgroup of GL3K. So in this case, we can have this short exact sequence. So have 20 minutes, right? So next, I will try to introduce the tool. So I think I forgot to change the name. So here it should be called Facebook Poisson variations. So what is a variation? So variation, which is what we know when we study algebra. So it's just a map from a field to an integer set, include and also union infinite. So satisfies the three condition. This is a ordinary valuation definition. But if we wanna put the information of Poisson structure, so we do need to add the condition for the bracket. So and the bracket for the item 3, there was two things is about it's try to sorry. Sorry, here is just the information, the definition of a variation. Next, let's go to the give an example. So this is the first example when we study variation from textbook. So for example, if my group is just the natural number field and P is a prime number, a P article variation can be defined in this case. Because for every rational number, we can write as p power times m over n. So and such that m p not divided the factor of mn. In this case, the valuation of a can define p article valuation of a can define as I. So for the Poisson variation case, first we start from a Poisson field, and then the last three condition plus an extra condition, which is a Poisson bracket. So how to define the valuation on a bracket of two elements, which is here we just need this valuation satisfies the inequality, and in this case. We can put we can get the Poisson W variation. If W choose to, I mean here W is just the integer, you can choose W as a 0, right? So here is an example. We still use the 3-variable algebra. The 3-variable polynomial algebra as well, Arcanine algebra, and we can define the valuation in this case because this algebra is a grid algebra, and then we can just define the valuation. Every element you can write as a sum of different degree pieces, right? So here let's assume n is smaller than m, smaller or equal to m, then there's two different valuation. One is the identity valuation, which is choose the smallest number of the pieces, and another one is the negative identity valuation, which is choose the negative m. In this case, okay, but we definitely these two maps are Poisson variations. And then use the so valuation is also very negative to the filtration. So if we have algebra or here for Poisson algebra, then we have a filtration. This filtration is just to use the regular definition. But if we want to put the Poisson, then we only need to add the condition of the bracket. So the Poisson bracket of Fn, Fifg must satisfy this information. Here, basically we can try to ignore the W. W is just the infinite. So in this case, for example, we can if we have because our algebra, polynomial algebra has a degree, then we can use the degree to define the filtration. And in this case, by this definition is a Poisson valuation. Okay, so those just the terminology. And next I will introduce use the filtration to define the associative graded algebra, which is just use the normal terminology to define the growth A. But for Poisson case, we just need to make sure the Poisson bracket and the filtration should be compatible. So in general, because A is a polynomial ring, and in particular in our case, A is a domain. So we want to have to do the growth associative, take the growth associative algebra. So it's still a domain. So in this case, we call such kind of filtration as a good. So next, finally, I will use those terminology to introduce our the definition of our tool. So if Poisson valuation called faithful, it satisfies the three conditions. So the image of mu is it should be whole set of Z and the union the infinite. The GK dimension will not change after you do the growth associative algebra. And then in particular, this bracket will be non-zero in this growth associative algebra. So in this case, we call our Poisson valuation is faithful. Okay, next is the part I'm very excited to share also how to use the faithful valuation to understand the this isomorphism. So as I said, if we know automorphism is graded, then you don't have too much choice. Basically, it's just a matrix, right? It's just a matrix. So this step is the case steps for how to understand the Poisson automorphism. So here is the key. The key is that if we take the fraction of P omega, and P omega, which is just a module the mod out the ideal generated by my omega. So the key fact is that for this Poisson algebra only has two faithful zero valuation. So here you can just ignore zero, just the two faithful valuation, which is just mu identity and mu negative identity. So that's the key part. Now we will use the key part to understand the automorphism group. So suppose I have an automorphism phi, then we can extend it to the fraction field Q. In this case, you use the group automorphism the automorphism group act on the two number set mu identity and mu negative identity, which should be get the same set, which is to say, and then we can use the fact by the definition of mu identity and mu negative identity. An element A is cohomogeneous if only if the mu identity A act on A and the mu negative identity act on A equals 0. Because of this is just use the definition of a mu identity and mu negative identity. So in that case, we can show that for every homogeneous element A, phi A is again homogeneous, which is step 5 is just given by step 4. So this is just to tell us at least my phi for any automorphism is just greater or equal. And then in particular, next we just need to fix the what's the degree of the image. Step 6 just tells us here x, y are the general of our algebra. So we just need to understand what's the grade of phi x, phi y, phi z. So by this equation, we can easily to see that the image of phi x, phi y, phi z we are not changing. So this is just to tell us phi is a degree zeta, which means which just show this group automorphism greater Poisson automorphism, which is just greater Poisson automorphism group, which is isomorphism Poisson automorphism group. And okay, so the last part I want to say, let's go back to our original motivation. So we want to understand what's the pivotal automorphism, right? So in our case, here, if my give a condition to my omega, say omega has a degree which is equal A plus C plus C, we can do a classification under the up to isomorphism. So all of omega has a two big family. One case is a reducible case, another case is irreducible. And for the irreducible case, we have definitely 5 cases. So now case 1, we know that what kind of for case 5 we know for case 1 we know the automorphism group, right? For case 2 and 3 and 4, 5, actually we have some ongoing result, but we are not presented here. So because it's not finished yet. So after we finish all the, understand all the type of Poisson automorphism group, then we can go back to our original motivation questions, try to understand the pivotal automorphism, and eventually we want to say, once we know all the pivotal automorphism, can that help to complement of the automorphism group of polynomial? So that's all my talk. Let's stop here.
Thank you very much. Are there any questions? Can you show us the last theorem?
So one of the key things about Thiem automorphisms is that the group of Thiem automorphisms is the amalgamated product of a pluripotent group and GLM. So do you know what will be the structure of the group of all pivotal automorphisms in terms of some amalgamated products of groups?
That's very good question.
Oh.
I think somehow we don't know yet, because actually our definition say only fix to irreducible polynomial, but so this is relative weighted and natural polynomial, so it's not quite clear like what the polynomial matrix, the matrix form.
There are no other questions. Let's thank you. Yeah.